Hi guys, welcome to my channel. Before we get started, make sure to hit that like button and also subscribe to my channel. MIT researchers develop AI system to design and 3D print robots, so make sure to watch the full video. New materials with unique properties that can be used for 3D printing are constantly being developed by scientists and engineers. However, it can be difficult and costly to figure out how to print with these materials. To consistently print a new material successfully, an expert operator frequently must use manual trial and error, and possibly thousands of prints to determine the ideal parameters. These boundaries incorporate printing pace and how much material the printer stores. MIT scientists have now utilized man-made brainpower to smooth out this strategy. They created a machine learning system that makes use of computer vision to observe the manufacturing process and then, in real time, corrects errors in the way it handles the material. They taught a neural network through simulations how to reduce error by adjusting printing parameters, and then they put that controller on a real 3D printer. All of the other 3D printing controllers, they compared it to printed objects with greater precision than their system. The work avoids printing thousands or millions of real objects to train the neural network, which would have been prohibitively expensive. Additionally, it might make it simpler for engineers to incorporate novel materials into their prints, which could aid in the creation of items with unique chemical or electrical properties. It might also make it easier for technicians to make last-minute adjustments to the printing process in the event that the environment or materials change unexpectedly. Plastics, metal, glass, and even food are now included on the list of materials that can be printed three-dimensionally. With the development of a system that can three-dimensionally print the fundamental structure of an entire building, researchers at MIT are currently adding to the list. According to the researchers, structures constructed using this system may be produced faster and at a lower cost than is possible with conventional construction methods. A building can also be completely tailored to meet the requirements of a specific location and the needs of its creator. Indeed, even the inward design could be altered in new ways. As the process progresses, various materials may be incorporated, and the density of the materials may be altered to produce the optimal combinations of strength, insulation, or other properties. The researchers assert that, in the end, this strategy may make it possible to design and construct novel types of buildings that would not be possible with conventional building techniques. The mechanical framework is depicted for the current week in the diary Science Advanced Mechanics, in a paper by Stephen Keating, Ph.D. 16, a mechanical designing alumni and previous examination offshoot, in the Intervened Matter gathering at the MIT Media Lab. The two research assistants in the Mediated Matter group, Julian Leland and Levi Kai, and Neri Oxman, Group Director and Media Arts and Sciences Associate Professor. A large industrial robotic arm is carried by a tracked vehicle, which also carries a smaller precision motion robotic arm at its end. After that, any conventional or unconventional construction nozzle, such as those used for pouring concrete or spraying insulation material, as well as additional digital fabrication and effectors, such as a milling head, can be directed by this highly controllable arm. This free-moving system can construct any size object, in contrast to typical 3D printing systems, most of which use some kind of enclosed, fixed structure to support their nozzles, and are limited to building objects that fit within their overall enclosure. The researchers used a prototype to build the basic structure of the walls of a dome with a diameter of 50 feet and a height of 12 feet as a proof of concept. This project took less than 14 hours to print. The foam insulation framework that was used to construct a finished concrete structure was made by the system for these initial tests. Polyurethane foam molds are filled with concrete in this construction method, which is similar to traditional commercial insulated concrete formwork methods. Following this methodology for their underlying work, the specialists demonstrated the way that the framework can be effortlessly adjusted to existing structure locales and hardware, and that it will fit existing construction laws without requiring entirely different assessments. Keating makes sense of. In the end, the system is supposed to be independent. It has a scoop that can be used to both get local materials, like dirt for a rammed earth building, and prepare the building's surface for construction. Even with solar panels providing power, the entire system could be operated electrically. The thought is that such frameworks could be conveyed to far-off locales, for instance in the creating scene, or to regions for calamity help after a significant tempest or tremor, to quickly give strong sanctuary. A definitive vision is from now on to have something absolutely independent that you could ship off the Moon or Mars or Antarctica, and it would simply go out and make these structures for a really long time, says Keating, who drove the improvement of the framework as his doctoral proposal work. However, he adds, we also wanted to show that we could build something tomorrow that could be used immediately in the interim. That is how the group managed its underlying portable stage. With this interaction, we can supplant one of the critical pieces of making a structure. At the present time, he says, it very well may be coordinated into a structure site tomorrow. The development business is still generally doing things the manner in which it has for many years, says Keating. The buildings are rectilinear, largely constructed using standard blueprints, and the majority of them were assembled with saws and nails. But Keating wondered if on-site environmental data could be used to design each building individually. Later on, the supporting mainstays of such a structure could be put in ideal areas in light of ground-entering radar examination of the site, and walls could have changing thickness relying upon their direction. In cold climates, a building might have walls that are thicker and better insulated on the north side, walls that taper from the bottom to the top as their load-bearing requirements drop, or curves that help the structure withstand winds. The Mediated Matter Group's overall goal of designing buildings without parts was the impetus behind the development of this system, which they referred to as a Digital Construction Platform (DCP). Such a dream incorporates, for instance, joining design and skin and pillars and windows in a solitary creation process and adjusting numerous plan and development processes on the fly as the construction is being fabricated. According to Oxman, the project challenges traditional building topologies such as walls, floors, or windows, and proposes that a single system could be fabricated using the DCP that can continuously vary its properties to create wall-like elements that continuously fuse into windows. Oxman views the project from an architectural point of view. To this end, the new 3D printing system's nozzles can be changed to change the material's density, and even mix different materials as they go. In the rendition utilized in the underlying tests, the gadget made a protecting froth shell that would be left set up after the substantial is poured. That foam surface could have interior and exterior finished materials applied directly to it. The framework could in fact make complex shapes and shades, which the group showed by including a wide, implicit seat in their model vault. Before the concrete is poured, any necessary wiring and plumbing can be inserted into the mold, creating a finished wall structure simultaneously. Using built-in sensors for temperature, light, and other parameters, it can also incorporate data about the location gathered during the process to adjust the structure as it is built. According to Keating, the team's analysis demonstrates that such construction methods could produce a structure more quickly, at a lower cost, and with greater safety than current methods. This system requires less hands-on work than the construction industry, which is one of the most dangerous occupations. Additionally, rather than having to match what is available in pre-made lumber and other materials, the total amount of material required could be reduced because shapes and thicknesses can be optimized for what is required structurally. Oxman points out that the platform is an engineering advancement. One thing is to make it faster, better, and less expensive. However, the ability to design and digitally fabricate multifunctional structures in a single build exemplifies a transition from the machine age to the biological age, considering the building as an organism that is computationally grown, additively manufactured, and possibly biologically augmented instead of a machine to live in. She states, "So to me it's not just a printer, but an entirely new way of thinking about making that facilitates a paradigm shift in the area of digital fabrication, as well as for architectural design." Case in point.